And you guys can see that now the covariance matrix, the whole covariance matrix, captures very well what we're looking for. It captures the variance and the direction of the data, okay? So somehow, finding that projection axis, it should leverage and use the covariance as a metric, okay? Now, how we do that? Let me just remind you guys of how we found the covariance here. So this is a good reminder. And here, let's say we have a matrix. So this matrix, sigma, it belongs to RD times D. So it's a D-dimensional matrix, which means our matrix sigma has D times D elements, okay? And then here what we are computing is the ith element, the ith feature or dimension. So this is feature I. And then we take also feature K. And right here at their intersection, we compute sigma of IK, their covariance. How do we compute their covariance? It's actually very simple. If you can get this, you can, basically you'll never forget what covariance is. So let's look at this data first. So this is my data, right? So these are the number of my samples. I have n samples, and I have then d features. So what the formula is telling us, it's basically we will take for each sample j. So for sample 1, for example, right here. So let's take the first sample. For the first sample, what we're multiplying two different features, like, the feature I and K. So this is the feature I and K. But across, we're multiplying and summing across all samples. So let's do this. So if we look at this matrix, what we are doing, so here there is one thing that I excluded, which is the mu, the mean. So sometimes the mean is equal to 0, but other times it's not equal to 0. Okay, so in this case, let's say it's not equal to 0. How do we get the mean? What is the mean? The mean mu I is actually the mean of feature I across samples. So let's look at this. So here, these are all your samples, and this is feature I. So what you need to do is just compute the mean of this column vector, of the ith column vector, basically summing all those elements and dividing them by the number of samples. So we're computing the mean value of the feature I across all samples. So this will give us what? Mu I, okay? Now we do the same for the other one. So by summing all those elements, the values of the features across samples, the kth feature, we get mu k, okay? Now, what we need to do next is basically, it's quite simple. So we take, let's look at this formula. So we take each element here. So for example, we take the jth sample. So this is the jth sample. And then for the feature I and K, I subtract mu I. And from the other one, I subtract mu K, the average. Okay, and then just multiply them. I just multiplied them. And then the next step would be to go to the next sample and add. So it's a summation over all samples. So I go to the next sample and I do the same. So this is the next sample. I subtract the mean, right? And from the second feature, for the kth feature, I subtract the mean of the kth feature. And I multiply, basically, the features of the same sample. That's it. That's what we were doing earlier, okay? So it's just, basically a multiplication of, a row-wise multiplication of these column vectors. So we multiply and sum until the last element, and that's how we get the covariance here between the ith feature and the kth feature of our data, this element right there. Okay, great. Now, there's one thing very important that from now on we will consider, which is called centering the data. So let's look at this here. So what does data centering means? So data centering is an important step. It actually helps you get rid of this mean the mu that tags along. So you want to kind of remove it from all of your equations. So this is called data centering. It means your data will be centered a lot around mu equals to 0 for all features or along all dimensions, okay? So for example, here, you look, this is a non-centered data because, you know, the mean is, you can see the mean of this data. If I plot it, the average might be located around that point. So the mean is different from 0, 0. In this case, it's different from, you know, it's different from 0, 0, right? For these data points. So our goal is to center the data around the mean 0, 0. So I want the mean to be exactly located at 0, 0, okay? So this is the basic idea. So why we do that? So here, for example, non-centered. And then if I copy paste this, so this is after it's centering. So the mean here, let's say the mean here is different from 0, you can see, okay, if I have two different features. And right here, it's the mean is exactly 0, 0, okay? Great. So how to do that? It's quite simple. So what we can possibly do is take this matrix, and then there are different ways, but I can compute, like define another matrix of exactly the same size, probably easier to copy paste. So I take this matrix and I have the same size, and then here in these rows what I will put is mu I along all dimensions. So all of those are mu i's, and I perform an element-wise subtraction, okay? So, and this is mu k, these guys. So if I put it this way, so this is mu k, the mean of all features, because at the end I want to retrieve these means, if you guys remember. So I want to subtract this from all those elements. So it's just an element-wise subtraction. So if I do this, then I will get an x-centered. Okay, you guys got that. But you can do it in different ways. But this is a simple way. But you can do it in many different ways. So your x-centered will be this data. Okay, great. Now let's look at how we will update this covariance basically formula. So here we want to compute the same thing, but what we will have, the mean will be equal to 0, right? Because for the new center data, if I have a center data, this mean will be equal to 0. So then I just need to remove it, and I remove this one. And now you can see very nicely how we get the simple product between features when the data is centered, okay? So it's very simple. And this is actually very neat and simple for like formalization of covariance. And remember, guys, we have a, each sample belongs to RD. So this is just an element, okay, in your covariance matrix. This is the covariance between the ith feature and the kth feature. Okay, now one thing even more exciting, and this is actually something that makes a lot of problems a lot easier. So now we know that covariance holds the solution for us, right? And we know how to compute the covariance, but still you need to do all these summations. It's a bit tricky. Sometimes the data is not centered, so you need to do this, right? Compute all this formula. There is even a more direct way in doing this using linear algebra, and I will let you guys just verify this. So here, what is the algebraic form of sigma for a centered data x? So we have our x data, it's centered, and here it belongs to R&D. It turns out that this is exactly the formula that we have. This is, like the formula for these covariance. It's x transpose times x, right? Very simple. And we divide by what? We divide by the number of samples. So you guys can remember this always. So here, imagine we're gonna verify it for just a few elements. So first, let me ask you a question. So what is the dimensionality of this covariance here? So remember, this one is d times n because I transposed it, and the other one is n times d. So when I multiply, this dimension will disappear. So we will get d times d. Okay? Right? And then now let's verify this together. Let's look at this data set. So here we have only 2 points, 2 samples, right? And these samples, they have 3 features, right? So we have 3 features for each sample. So this is a 3-dimensional space, feature 1, 2, 3, dimension 1, 2, or 3. Now, if we compute this, I will give you just a minute, and I would like you to start computing this to verify that xt transpose t, x transpose x is actually will give us this one. So let me just copy this one. And so it should be exactly the same. So remember, so this is a 3 by 3. And along the diagonal, what do we guys have? We have the variances of each feature, right? So this is, variance of feature 1, which is, this is variance of feature 1, variance of feature 2, and variance of feature 3. Okay, guys, so I think it's kind of pretty obvious. So here, if you compute sigma of 1, 1, what do we find? So we divide by the number of samples. Sorry, so we have 2 samples actually. Yeah, right. Number of samples. So we have 2 samples, okay? And then we take, so this is sample 1, we multiply the, like we multiplied exactly with the same feature, because here it's 1, 1. So feature is like I equals k equals 1, 1. So it's like x1 squared plus the second, we go to the second sample, which is y. And here for the second sample for j equals 2, right? We have also y1 squared. So you can do it. It's very straightforward. Now let's look at 2 interesting examples. So here we have the first row, x transpose. So we're going to multiply this row, but the second column. So this will give us element 1, 2. So element 1 and 2, it's this element, right? And what we find is x1, x2 plus y1, y2. And this is exactly, the product of the coordinates or the features for the first sample, for sample 1, and we do it for sample 2 and we add them up. Is it clear? Right? Very clear. Okay, cool. And then the last thing is we have it for also, for example, 2 and 3. 2 and 3. And here, guys, you can notice that this is exactly the covariance of the center data. Right? You will never forget this. X transpose X. Great. Now, so remember why we're doing this. Guys, why we're doing this. What is our goal? So we are looking for the metric to learn how to find the projection axis, right? That maximizes the variance of what? Of the projected points. Maximizes this breadth, this the distance, right? The breadth of the projected points, the variance of the projected points. So we found that the covariance is a very good metric. We can use it to solve this problem, okay? Now, let's look particularly at the covariance of the data itself, the covariance sigma of our data. So we have n samples, X transpose X. And let's see how using this covariance, we will be able to discover this axis. Okay, how can we do that? Now I'm going to give you intuition. Right, so here, very few steps. So what we have first, we need to center the data. So this is the center data around 0. Okay. Next, we define data covariance. So the data is centered around 0. So this is the covariance of the data. So we have 2 features. So it's a 2-dimensional covariance. And this is a very kind of intuitive covariance for this distribution of the data, because you can see that there is more variance along this axis, the first one. Okay, now the next thing is, this is, just to derive the intuition. What we will do, we will define a linear transformation using sigma. So if you guys don't know what a linear transformation, I'll explain. It's very intuitive. So sigma is a matrix. We can use, this matrix to map a set of points in the original space, okay, to a new space, a transformed space. How can we possibly use this sigma, okay, the covariance of this original data, to transform the space, to stretch the space? So to do that, basically, the idea is quite simple. So for each point, what we need to do is define a linear transformation based on this matrix. So the linear transformation is encoded in this. So it's just, you can think about it as a change of coordinates. Have you seen linear transformations before? Okay, just very few. Okay, so basically here, what we have, imagine we have a vector. So given a point P with coordinates x and y, it can be any point in the original space, right? We want to map it using the covariance matrix, okay? So to map it, we simply take the covariance, or our mapping matrix, let's call it, and multiply it by the original vector, and we get the mapped vector, which means we get the new vector right here with new coordinates, okay? So for example, How do we find this? So let's say this is my sigma, and I have my vector, my point xy. So the linear transformation will be defined as, you guys can see, so it's the first term is like 9x plus 4y, and the second coordinate gets mapped to 4x plus 3y. Okay, so this is the mapping function. So if I do this, I take a point. For example, let's take the 0, 1. What is the, if we map it, transform it using the covariance, what are the coordinates of the mapped point? So it's just, you need to plug the coordinates of 0, 1, the x and the y, just replace the x and the y, and you'll get the new coordinates. So if we do that, we will get 9, so that's a 0 times 0 plus 4, so that's a 4 for the first coordinate, and for the second one, that's 4 plus, that's like a 0, so 4 times 0, okay, plus we have 3 times 1, so that's a 3, okay, so which means that this point right here gets mapped to this point right there. So we will do this basically to each point. So negative 1 zeros gets mapped to negative 9, negative 4. We have 0, 0 remains the same, so it's a stable point. 0, negative 1, it's, negative 4, 3, etc. So here, what is the point? Why I'm showing this? So I would like you to know that basically, when we are deriving the covariance of this matrix and we're applying it to some points in our original space, what is it doing to this space? So somehow, this is the original data, right? It's located around, like inside this, maybe a circle or sphere. But if you look at the transformed points, so you can see that the covariance matrix, when we use it to map the data, it somehow stretched the space and rotated some points, okay? So this is what we call a linear transformation. Now, what's the point? Why we're doing this? This is the reason. So basically, when we use the covariance of the data X, our covariance matrix, and somehow we try to map, we map different points, different vectors using the covariance matrix, we notice something very particular. We notice that for some particular directions, directionality, so remember, we're looking for a projection, right, for the directionality of the projection. We notice that for some particular directions, like these ones, okay, when we map them, the direction remains the same. They do not change. But other directions, so this one also, these two particular vectors, they remain the same, so we have the same direction. There is something particular about them, but all other points or all other vectors, if we want to map them into this space, they will have different positions. But there are some particular vectors, when we map them through the covariance matrix of the data, they remain stable, okay? These are good directions. So now let's look at what are those. So here, this is, for example, the direction, the particular direction or special direction u1. Let's call it vector u1. This is the vector with coordinates 2, 1. And we have u2 with coordinates negative 1 and 2. So when we map these two vectors using the covariance matrix, what does it mean? It means like we take the covariance, multiply it by the vector, get new coordinates, right? Get new vectors, basically. So what do you guys notice when we computed this? So here, these values are very special. So what is the relationship between these two, and what is the relationship between these two? So these are identical for the second case. So here we get something like 1 times the original vector, negative 1 and 2. But for the other one, we just scaled the vector because this is an 11, so times 2 and 1, okay? So what we did is just scale the vector. But as you notice that these two vectors remain almost unchanged by the covariance matrix, and these are what we call them in mathematics eigenvectors, okay? So this is an eigenvector, okay? So eigenvector 1 of what? Of covariance matrix of sigma. And we have another eigenvector 2 of sigma. And we have what? We have the scaling value, which is very important here. So 11, this is a large value. So here, this is what we call the eigenvalue associated with the first eigenvector. And we have another eigenvalue here of 1. So it turns out that basically what we are looking for, right? So if you guys look now, if I plot the coordinates of the eigenvector, I take this eigenvector 2, 1, and it's a 2, 1, so it's right there. And my second eigenvector, but I scale it so it's like, you know, a large one because it has a value of 11 here, eigenvalue of 11, here eigenvalue of 1. What do you guys notice? When I take the eigenvectors of the covariance matrix, I found what I'm looking for. So here, this is the first axis, right? If I project all my samples onto this, you know, axis, let's call it U1, okay? So then this is basically the best axis that preserves the maximum variance of the data. Well, I should have done it in red because this is, okay? Now the second axis, it's the perpendicular direction. This is the second eigenvector, right? And when I project the data onto this one, along this direction, this also maximizes its variance. But you can see the first one captures everything. So basically, what we're looking for was, first, we couldn't use the mean. So the mean was not a good metric. The variance alone was not the good metric. Now we looked at the covariance. Let me write it here. Okay, which is x transpose x. And we discovered that the eigenvectors and values, the eigenvector, here it's with having the largest eigenvalue because 11 is larger than 1, right? With the largest eigenvalue is actually what we call our principal component, or the projection axis that we were looking for, okay? So just to sum up the whole story from the beginning, this is the algorithm. And here, first thing, how we do PCA, looking for the principal components. First, we need to center the data around 0. So this is the first step, center the data around the mean 0. Then compute the data covariance matrix, right? Next, we use to find the eigenvectors. So this is by chance. We found them by chance, right? But there is what we can use singular value decomposition, SVD, singular value decomposition, to automatically find those eigenvectors and their corresponding eigenvalues, okay? And after doing that, to find the eigenvectors and eigenvalues of the covariance matrix, we need to sort the eigenvectors by their eigenvalues from large to small. So we pick the ones with the highest or largest eigenvalues. These are the principal components. So remember here, the one which had an eigenvalue of 11 has preserved the maximum variance of the data. So this is why it's called the first component, because it preserves the most information about the data. The second one preserves less, but it's still meaningful, okay? Now, the next step, we need to select. So up to here, we just mapped the data, right? So next step would be to select the top k eigenvectors or dimensions, along which we will project the data. So if I select, so let me ask you a question here. If I select the red one, only the red one, so this is, basically my new dimension. So if I have k here, d equals 2, I have two-dimensional data. So the maximum number of eigenvectors that I can have is 2, right? So if I select only 1, then what is the dimensionality of the map data, of the projected data? So if I project everything onto only the red axis, 1, very good. Now if I select the red axis U1 and also I select U2, Okay, and I project the data onto this. So I can project it and I can have new coordinates, right? So the coordinate of this point, now it's getting all mixed up. Okay, so the coordinate of this point right here, it will be these 2 points in the new coordinate system. So I have a new coordinate system, right? So this is maybe 2 and 1. So everything has changed, but still, did I reduce the data if I project onto these 2 axes? No, because originally I have 2 features, and when I projected, I also had 2 features, but these are 2 new features. I extracted 2 new features. So I did not perform any dimensionality reduction. So for this case, we need to select K, with K generally being what should be smaller, right, than D, the number of the original features. Now, the next step would be to represent the data projected into a low dimensional space, right? And then, yeah, so after doing that, we transform the data using these, we transform it using or project it using the K eigenvectors into the new space, and this performs dimensionality reduction. Now, these are the key steps of PCA. We're going to have a break, and I will explain why we're getting eigenvectors, why we're getting eigenvalues, because all of this up to this point is just based on a few sketches and some intuition, but mathematics gives us awesome tools to solve this problem. So we can, using optimization, we can discover that basically the eigenvectors with the largest eigenvalues are the axes that we're looking for. Okay, so let's have a 10-minute break and then we'll be back.